which is changing a paradigm shift. We can say that is a paradigm shift in the total energy sectors. So I will cover why this has happened and what is current situations in the market, especially I'm talking about the Indian sectors because I'm being witness of the sectors from last 6 to 7 years. It's getting changing. Probably there are multiple reasons. Then we will also cover what will be the future energy looks like. Um, so my presentation's not so fancy, but I try to cover. I will talk more on the data and the numbers and the reasons for that change. So there are some numbers which may not be accurate, but it gives the feelings that where we are going. So with that, I will start my presentation. So we all use energy. Mainly, I'm talking about the electricity. So uh, the image on left and right, you can see here the famous person, the founder of GE, Thomas Alva Edison, who invented bulb in 1879. That's electric bulb, and it's a revolution in electricity where we started using electricity as a source of energy. But that was not like start point. The other start point was the other image on your left side or right side. That's in 1884, Mr. Charles Parsons from the Parson company, where he started this company, the steam turbine. So the commercial use of the steam turbine started by the Charles Parson. He invented. We all know this reaction grade, 50% reaction grade steam turbine in UK, and this was the option for earlier we were using the reciprocating engine. So there is a way to improve the efficiency, reliability, and all those things. We started using steam turbine mainly initially for marine applications, where he used the steam turbine to drive the uh, boats and submarines, and then also used the steam turbine for generation of electricity. So if you see orally the picture, the mostly we use fossil fuel from almost 120 years, fossil fuel in terms of coal or whether gas, whether it's hydrocarbon or other source, like you can say that LPG. So these all things are known as a fossil fuel, and we are using fossil fuel from 100 years. So why we are saying that we need to change our source of energy or we need to shift our paradigm? So we all know that fossil fuels are emitting greenhouse gases, which is not good for us, not good for planet Earth. And we see the change in the temperature, change in the atmospheric behavior pattern, weather patterns. And on 9 on 2016, almost more than 196 countries, in fact, ready to agree that we need to reduce our atmospheric temperature by 1.5 degrees Celsius by 2050. So that is our target. So we need to reduce our greenhouse emission gases. Uh, so from 2016, I would say the entire energy sector changed, and it changed a lot. Um, it was like drastically changed. It is change of not only the change for manufacturer, but it's change for government, change for user, and it is in transition phase. It is not happen 100%. We know that, but it slowly, steadily is changing, and that is what we are going to discuss today. So, uh, as I said, greenhouse gases. So here the pie chart shows that the different country that are generating greenhouse gases. So here you can see 28%. China is a maximum contributor towards these greenhouse gases, and then USA, and then India. So India basically is on, I would say, third place. But per capita, if you see, then because we have large populations, so it's on number 7, I guess. But still, as India, we are contributing towards this climate change, and that has to be changed because every country agree on that we need to reduce these greenhouse gases or temperature. So whatever ways we are using currently as a source of energy, that we need to change. So as I said, the this is the per capita uh, CO2 emission, and the countries like USA and Canada, they are the one of the toppest or one of the highest on earth which are emitting or generating greenhouse gases. And in terms of populations, India comes somewhere around here 5 trillion metric ton CO2 per year. So if you split the sector wise, that which sector is contributing more in greenhouse gases. So I have a data of USA. I couldn't find data for India, but it gives overall picture. Everywhere it's the same. And the most of the greenhouse effect came from carbon dioxide. It's a 65% contributions. Apart from that, you have carbon monoxide, methane, nitrogen oxide, other gases like refrigerant, F gases, we call it refrigerant and all those things. But the carbon dioxide generating from the burning of the fossil fuel, because ultimately fossil fuels contain the carbon, and carbon when it reacts with the oxygen, it creates carbon dioxide. So if you divide in a sector wise, then the image over says that the 25% carbon dioxide coming from the electricity what we are using currently, and the rest, if you see the industry, so industry means whether it's chemical industry or it's a steel industry, automobile industry, they are also using electricity. They have their own captive power plants, they have their own process, so they also consume a lot of electricity. So this electricity is directly coming from your power plant burning fossil fuel, but then other source is also significant, is the industry. And then transportation, because we use car, bike, buses, train, aeroplanes, all use right now um, hydrocarbons. So this all sectors are now getting affected, and we are witness right now. So we see there is changing happening over there. So if we need bring down this 1.5 degrees Celsius, then we have to change our source of energy. So there is a one more way to present that the energy means whether it's automobile energy, whether it's energy used in industry, the hydrocarbon right now, sorry, carbon dioxide right now, 73% is coming from that source of energy. So mainly this coal and hydrocarbons. So this is global picture, what I said. Now I will talk about the India power sectors because I'm closely monitoring these sectors, and we are part of this sector also. So we will talk a lot about the megawatt. When we talk about the power plant capacity, we typically says kilowatt megawatt. So we call megawatt. Megawatt is the unit of the electricity, also unit of the power. So 1 kilowatt is equal to 1.34 horsepower. A car engine produces 100 kilowatt, right? A railway locomotive is 1.5 megawatt consumed. And large steam turbines we have in India up to 800 megawatt capacity. So that's a huge power. And if you compare with our household equipments, then we consume like bulb 60 watts, computer screen 200 watts, boiler kettle 2 kilowatt, AC 3 kilowatt, you know. And large city like big cities, normally they need 500 megawatt to 1000 megawatt power every day, every time. And 1 megawatt normally supplies to In India, roughly around 900 house, the consumption of the 900 house. So each 900 house consume 1 megawatt electricity. So it will gives you idea that what we in India using consuming this electricity and what is our capacity. Our capacity to produce uh, electricity, the total capacity is roughly through 375 gigawatt. So in India, we consume 375. We have capacity to produce 375 gigawatt. And this is a breakup. If you see, uh, the black part shows the coal. Our main source of the electricity in India currently is the coal. Because the simple thing is we have large reservoir of the coals in central part of the India, Madhya Pradesh, Chhattisgarh, and there are other states. We don't have the gas. So most of the electricity or the power coming to our house are coming from mainly a coal-based power plant. There are gas-based power plant, but very few because we don't have a gas. We have to import gas from uh, this Gulf country or Iran or Venezuela. It is costly because transporting the gas also costly and the gas itself also costly. So uh, the 53%, so approximate 2 lakhs megawatt capacity came from the coal. And then this is the graph over a period of time. So let's say after independence, we started using mainly a coal as a source of energy. And in initial days, those power plants are also small. We had mostly the collaboration with the Russian government, where we import uh, boiler and turbines, steam turbines from Russia. The company name is LMZ, and the capacity is 90 megawatt to 110 megawatt. And then slowly that capacity increased to 210 megawatt up till this point. And that was again coming from Russia. Then our government decided to, change that. We should have a balance in politics. So they started importing uh, the steam turbines and boilers and other components from Germany. So that means Siemens. So we Siemens had a collaboration with the BHEL that we will supply a design to the BHEL of a 500 megawatt machines. So earlier it was 210, now it's a 500 megawatt machines, and BHEL started manufacturing those 500 megawatt machines and supply across all India. So that ways you can see the demand was that time increasing because population was increasing, industrial growth was increasing. To fill that demand, to fill that gap, the five bigger machines were started installed, and it was continuously installed. 500 megawatt machines continuously installed till you say I would say 2005 or 4 time period. But then there was an economic boost in India. So definitely you need large power. So we need alternative solutions. And the turbines and boilers, earlier it was mainly subcritical. Subcriticals means they are low in pressure, high in temp, like 540 degrees Celsius and roughly around 180 bar capacity. So efficiency was low, but then uh, there was new R&D happen in the steam turbine that we can go up to supercritical pressures, which is beyond 230 bar and 565 degrees Celsius. That way you can improve efficiency of the overall power plant and reduce the carbon emissions. So in India, the huge demand by like increase because of the economical growth, and we need to provide this new technology So Siemens has a collaboration with the VHL, and then other player also started coming in India like G Alstom. Then in 2008-9 periods, Toshiba, and they had a collaboration with the JSW. They were also supplying the steam turbine. MHI, Japanese company, they also started collaborating with the L&T, and they were also supplying the steam turbine. And the most of the development in 2005 onwards happens in a coal-based power plant. So you can see the exponentially graph increase, and the new machines were installed. Many machines were installed, mainly capacity of above 600 megawatt to 660 megawatt, and few are in 800 megawatts also. Uh, then same times, hydro was also growing. We had a dam over here, so you can see over 50 gigawatts coming from hydropower plant. But in India, we had a change in renewables energy after 2004-5 time period. Uh, there we see some development over here. Wind and solar was steadily getting increased, and gas-based also power plant installed, uh, mainly in Gujarat. There was Torrent Power. They had Suzen, Uno Suzen, Degen, few in Mumbai, nearby some in Karnataka, but not much because we don't have a gas, as I said earlier. And the development in gas was not that high that you can see clearly over here. And from last few years, it's almost stagnant. In fact, few power plants are getting old and they will retire soon. So the change happens in a two sector, coal base and the renewables. And as you can see here, currently that the 22% energy coming from renewables, whereas 51st still 55% energy coming from the coal. And who are the main player? Who are the main player in this power sector, power generation in India? Top five companies: NTPC, Adani Power, Tata Power, JSW, and Torrent Power. These are the top five players. And currently, you can see the NTPC is the one of the uh, biggest player. They have power plant across all India. They are generating 62,000 megawatt, mainly based on coal and gas. So they also started, steadily now, right now, coming into the renewables by, you know, installing solar power plants. But the others are like Adani. They have a big power plant in Kutch, Mundra. Tata Power, they also have a big power plant in Kutch, Mundra. And then JSW across all India, they have power plants. So apart from that, there are other players also who are generating electricity in India. They are state-owned company, electricity boards like Gujarat electricity boards and so and so on. So uh, these are the top five players. Apart from that, I think there are some captive power plants, small size power plants, but uh, very, I would say, not so significant. But after 2016, this Paris Agreement, people start looking in whatever we are doing is right or wrong. Like a country like Germany, they declare that they have 84 coal-based power plant and they will going to shut down by 2030. And they don't want to use that coal power plant, even though they have large lignite-based coal mines over there, big mines. But they have decided to shut their all power plant by 2030, and they will introduce or they will invest more in a renewable rather than investing in existing power plant. And this is not only about Germany, there are other countries also came in this same way, like they want to reduce their emission because they want to reduce their emission as per the agreement. UK and USA also decided in the same way. And the company who are supplying this steam turbine and gas turbine and mainly steam turbine coal based. So like Siemens Energy and Toshiba, they have declared that they will not going to supply any new steam turbine equipments to the new power plant. So they will not going to support this energy business. Even though um, like Alstom G now is a G, they have also declared the same thing. I think they will not going to supply a new coal-based power plant. There are other players also there, but they will continue doing that. But main these two players across the worldwide, they will not going to supply new coal-based power plant. They will continue support existing customers, existing their power plants, but not new power plants. So this is a huge change, I would say, because we see that 10 years back there was sharp increase in the coal-based power plant, not only India but across other regions also. But now we see decline, and companies saying that no, we are not going to support you. So in India, uh, which company like supplying more equipment? Like most of the equipments, steam turbines in India installed by BHEL. They have technology of Siemens, so we support BHEL, and we as a Siemens also support our existing customers. So 137,000 megawatt are supplied by BHEL, and then there are other players, Chinese player mainly, Shanghai Electric, Dongfang, then Japanese player like Toshiba, MHI, GE Alstom, Harbin, Chinese, and some of the Italy like Ansaldo and Francis. So here you can say from 55% of the coal-based power plant, the BHEL is the equipment supplied was like 69%. So out of 55 of that 2 lakhs, roughly 2 lakh megawatt, 1 lakh 37,000 megawatt supplied by BHEL. So it's a big player in this currently, and it's BHEL is owned by government of India. They are supporting to the NTPC, to the state board electricity company. So how future will looks like? So how this new investment or new installations will happen in India? I'm talking about India only. So as we said, this roughly 53% of coal-based power plant over here, they will continue grow. And the reason being there are several power plant under erections, and they will going to uh, erect by 2030, 2027. So roughly around 50 to 70 gigawatt in terms of the units. I would say the 16 to 20 units, new units are going under erection. So going to install right now under erection they are. So up till 2030, we will see still growth in coal-based power plant. It is not that in terms of the percentage wise, it is not that high as earlier, but it will still grow. Uh, and there are other reasons for that I will cover in later slide. But uh, hello, can you please mute
Sir,
yourself? I think disturbance. Okay, thank you. So then we were talking about the renewables. So we were here right now in 2020, 21 is here, and they will grow. So government India has decided to increase their capacity till 2030. It should reach 175 megawatt, and currently it's roughly 90 megawatt. So from 90 megawatt to 175 megawatt, you have to reach in a 10 year. It's a big leapfrog jump, I would say. You need a lot of investment in that. So whatever the new investment will come, it will surely come in this sector only. it will not come in this sector. You will see a huge investment, and that is what we are seeing right now. So we see Adani, I think Sterlite Group, and there are many companies. They are more interested in renewables only. So they are installing either big photovoltaic solar power plant or solar PV um, setups, wind turbines. Mainly in India, we have onshore wind turbine. Onshore means you have wind turbines on land only, but we have huge capacity or we have huge potential in sea also, but we don't have that at the moment install any wind turbine in the sea. So offshore, we call offshore. Offshore wind turbines are very big and they can generate a huge electricity, but we don't have that at the moment. Maybe in future it will come, but the new investment will happen in this sector only. Well, hydro and gas, they will constant, and maybe in my view, the gas will be decline because the power plants which are getting old are not going to be replaced with the new gas-based power plant. So this is a good sign where we see growth in renewables. On the same time, we see a stagnant growth in coal-based power plant. But that is a something which is alarming situation also. And we will see in next slide why we see that. Because we cannot depend upon these two alone, right? So one more thing, the same slides that how they will grow. So if you see in percentage wise, then renewable market will grow approximate 10% at a year, where the coal-based market will drop. New power plant will not going to be installed, but there will be a growth in a service. So you need to still supply a component failure of like once the components fail, you need to replace by the new one. So that will still continue, but new component not going to be installed, right? So when I say the it's still growing, coal base is still growing, but there is other thing also we have to look here that in India, uh, this table shows that the most of the power plant are now older. They are older than, let's say, the life of when we design the turbines, we typically consider 25 years or 20 years of the operating life. So we have now power plants, many power plants, which are pretty old and they are going to retire soon. So roughly 40,000 megawatt is going to retire soon. So here you can see the plant which are very old. Some of the power plant old by 25 years, some of the power plant 30 years, 35 years, 40 years. These power plants are pretty new, which we explained earlier that these are the plant which are the supercritical power plant and these are the subcritical power plants. They are going to retire soon and they are not going to replace with new coal-based power plant. So uh, on the one side, you have increase in a demand, right? Demand will surely going to be increased because industries are growing, population is growing. Probably you will have electric car on the road, so you need electricity, right? You need electricity for so that the number of currently what is our capacity is 375 gigawatt. It will grow somewhere around 500 gigawatt in next 10 to 15 years. So you need to fill that gap, and that is not happening right now. Right now, whatever the focus is happening over the renewables, but the other sectors are like gas, hydro, and coal is not going to install, then how you will manage this balance? That's a question, and that answer we need to find because uh, here you can see here that is linear calculation shows that our future we need roughly 500 gigawatt from current capacity. Then one wind turbine currently in India available is only supply you roughly 2 megawatt only. So if you need to install, let's say 1,000 megawatt, then you need to install 50, 100, roughly around that wind turbines. and it requires big area, where coal and I would say the fossil base require not that big area. For solar also you need a large land. So we right now, let's say the biggest solar based power plant or the photovoltaic cells are going to install in Rajasthan, 5,000 megawatt I think, that is going to be installed by Adani, and also one in Madhya Pradesh. So yeah, they are growing up, but what happen when uh, you don't have the sunlight and you have rainy days? So you have to think about that also. So how this cost, the cost is also playing a major role earlier, I would say, hurdle for renewables. So here you can see this is a cost of US, and in India also more or less same. After this is the photovoltaic cell cost, and it drops drastically in 2020. And wind also reduced by, wind turbine size can be increased. So increase in the size, you can bring down the cost. So offshore, currently offshore means the wind turbine which is going to install in the sea, far away from the sea coastal area. Inside, like in the sea, you can make a big tower and you can install this wind turbine. Current size is around, I think, 10 megawatt. It can produce a 12 megawatt. One turbine of the wind turbine can produce a 12 megawatt, but the blade size, the one blade size is 100-meter long. So if you have a like three blade, the diameter will be 200 meter. So it's a very big tower. So you need a good foundation and all those things really require. So again, the coal, the cost of the coal and the cost of the gas almost stagnant from last few years, where the these costs are bringing down. And just to give you a feeling, these are not so accurate number, but you will give some feeling. Nowadays, the installing of one coal-based power plant of 1 megawatt, you need 6 to 7 crore rupees. So, for example, if you need to install 1,000 megawatt, you need 6,000 rupees, 6,000 crore rupees. And the generation cost right now is 4 to 5 rupees per unit. Roughly, this is a number. In some power plant which are old or efficient, they have this number is here and there, but this is the rough number. But the biggest problem with the coal, they are generating CO2, and 900 ton of CO2 uh, emitted by per megawatt. So this is the biggest problem, and that's a contribution to our global warming. Whereas on the other side, this is solar. 1 megawatt installation cost is 4 to 5 crore per megawatt. This will bring down by, I think this is going down in nowadays, and the generation cost is also going down because this require only installation cost. No operational cost is required. You need only cleaning and maintenance. That's it. You install it and it is generating you electricity. So no CO2 generations in generating electricity. I'm not considering anything for, while producing this silicon based photovoltaic cells, how much CO2 is generating. But at during the generation of the electricity, during the operation, they are not producing any CO2, and that is a good sign. So roughly we are consuming zero point 0.7 kg of coal per kilowatt. And as you can see, the cost is also going down if you compare with the coal. So this is a good sign, but we need to come with a large scale. So this is about overall picture. I mean, I said renewables is definitely growing up and it will grow. It should grow, which is good for our environment. The only challenge is how you will balance it. We should look for the other options also, and it should be balanced somewhere. Now, with that change, like 2016 change, what impact came on steam-based power plant, right? Because earlier we saw that number was increasing, most of the energy coming from the coal power plants was running fine, but now you have other options also, cheaper options available. So how steam turbines power plant they are impacted. So before going that impact, I will just explain you about the construction details of the steam turbine. So this is a steam turbine, looks like typically 660 megawatt supercritical steam turbine looks like this. Also 800 megawatt. We have couple of, I think, four 800 megawatts are already installed, or more than that, I think so. So one in our Gujarat also in Vanapuri nearby Dahod. So there also we have one big 800 megawatt machines installed and generating electricity. So this is HP turbine. This is HP rotor. The steam come from here. These are the valves, stop valves, control valves. The valves enter. These are the pipes. So boiler, the steam from the boiler come from here. The valves will open. The steam flow over here. This control valves control the throttling, and then steam enters over here. This is the rotor. The blades are installed on the rotors, and work done by steam on the blades. So blades started rotating, right? And then from here it will this is exhaust of the HP turbine. It will go into the boiler again, reheat, and comes again from the boiler over here. This is a IP turbine, stop valve, control valve. In IP turbine, it comes here. This is the inlet chamber of the IP turbine. This is double flow IP turbine. So the steam will flow half of the steam flow in this direction, half of the steam flow in the other direction to balance the thrust. And these are the blades. And again, steam, low pressure steams will flow through the crossover pipe. These are called the crossover pipes. And these are two LP turbines. Here you can see the big LP blades are there. And it will come in the LP turbines. You can't see the picture of the LP turbine, but the blade sections are there. And then from that, it will go to the condenser. So this is a steam turbine deck. And below that, you have a condenser over here. And again, from the condensation, it will go to the boiler. Through VFP, it will go to boiler. And steam will come, like the cycle will remain continuous. It's called the Rankine cycle. We all know that. So right now, we have very big steam turbine also available. The Siemens supplied for the one of the biggest steam turbine in the world for the nuclear power plant, 1,800 megawatt roughly, and the blade size is 28 inch. So it's a very big, 28 meters square. Sorry, so it's a very big turbine. And in terms of the pressure, right now we have steam turbine capable to run supercritical 350 bar, and the speed, the steam velocity at this blade is always in the supersonic. So it's a supersonic Mach 2, and it can produce, as I said, 1,500 megawatt. This is a real picture of steam turbines in the plant. So you can see HP turbine, IP turbine, 3 LP turbine. You can use 1 LP, 2 LP, 3 LP, depend upon the mass flow rate of the steam. This can be configuration based on the parameters, flow capacity, and power output. So some of the pictures, how the steam turbines real picture of looks like in the factory. So you can see this is the HP turbines casing getting this rotor is getting installed in the rotor in the casing. So these are the real blades, real rotor. These are the big bolts, joining plane bolts, right? And these are the IP turbine casings. So IP turbine have two casing, uh, outer casing and inner casing. So how they looks like, there's bottom half, top half, and this is assembly of IP turbine. And here I was talking about the big blades. So this is a person who's checking blades, and you can see over here these are the big blades, last stage blade we call, because there's no blade afterwards. And when it rotates, it's a 3000 rpm, because the mass of the blade is so high. the blades under the high stresses, very high stresses because of the centrifugal load. And uh, as you increase the size of the blade, the stress also start going to increase. And the most of the component are designed such a way that it won't fail, but it's close to their limit. So we in engineering do various calculations that includes finite element analysis, CFD, and vibration analysis, force response analysis, and all those things. So it's, you can see over here current component. So current means the 10 years or 15 years back, the turbine component are designed for operating parameters like once they start, increase the load and remain on a base loads. For example, 800 machines is designed for, let's say, it start, increase the load, remain on a 800 megawatt, or you can reduce load by certain megawatt, but not by so large. And here you can see the few components are close to the uh, yield or crack initiation. So they already design, you can say that for this load pattern, and they are under high stresses. Even blade also, you can see the blades are highly stresses over here. They start vibrating, so they have vibratory stresses. So what I'm trying to say, the component design with this load. Now that is change, and this curve will tell you. And this is a famous curve which is known as a duck curve. And why it is called duck curve? This is a generation of electricity. This is basically generation of electricity with the combination of renewable energy, mainly solar and solar, and other one is the conventional fossil-based energy. You can consider coal or gas-based, right? So this is electricity demand per day. Normally daytime you demand is high, and then again when it reaches to night time demand is high. On the same time, by generation, you know, uh, you have in a daytime, because of the sunlight available, you can produce electricity through photovoltaic cells. So you can produce maximum energy at the daytime, but as sun goes down, the energy generation of the energy going to be reduced. So this cycle is happening daily, right? And the gap between, if for example, if I have a gap, uh, some 1000 megawatt, and I am producing 1000 megawatt by solar, that gap can be fulfilled only by solar. So what that means? That means that I have to shut down my steam turbine or gas turbine at that period, because you cannot pump energy into the grid, otherwise grid will fail. So uh, that time, at the peak time, you have to shut your coal-based power plant. And as I said earlier, my plant is designed not for earlier when let's say 20 years back, 15 years back, it was mainly designed for this load. It was not designed for this kind of behavior. And this is earlier, this solid line was close to the solar, but as year passed, we are going to install more solar PV. This gap between upper line and bottom line will going to be increase. So that means that you can produce maximum electricity from solar at the daytime, but on the night time you have to have either backup with the storage, or you have steam based or gas based power plant, and that creates a problem. So my plant is designed for this load pattern, but now my operator or the power plant owner, they have to follow this load cycle. And the component which are already under high stresses, they will get cyclic load, you know, because the steam turbines mainly made for base load power plant operation. Now this comes under high stresses, and that will result in what? Low cycle fatigue, failure of this high component like blade will fail, or not fail instantaneously, but if you do these things on an average daily basis, then there will be a challenge to steam turbine component. And what will effect of that? That whatever energy in a night which I supposed to produce by a steam turbine or gas turbine, if my steam turbine is failed, that means I cannot run that, and then no energy will become in the night time. So this is a challenge at the moment because we are in the transition phase and we were not ready for that. So as a Siemens, we develop certain methodology like because we cannot replace the component, each and every component, right? It's very costly and you cannot do that. So what you can do whenever the plant is going to be operate, um, you do a maintenance schedule such a way that you can avoid those failure, or at least you should know prior to failure. So we are using diagnosis tools, a diagnosis method, various diagnosis method, and based on that, we Siemens provide a solution to the customers that hey, now you have to do this maintenance. It's a conditioning based maintenance or whatever you call it. So earlier it's a corrective maintenance. You fail it, you replace it, run it. You wait until component fail. But now it's not affordable for power plant owner, also not affordable because they have to operate. If they will not operate, they will make huge loss. And once they are under loss, they have to shut the power plant. And many power plant owners are under stresses right now. They are not making money. They are under stress. They have huge pressure to run the machines in a given time frame period. If they will not do, they will out of the business. So it's a do and die situation for them. And for them, they have to follow this practice. So uh, this is more in detail, but I will not go in much in detail. But typically for a steam turbine, we have fixed maintenance period, like we call it 25,000 operating hours. You have to open the machines, you have to inspect everything. If you find okay, you box up it, certain parts you have to replace. This is traditional inspection method, or we call it the current inspection method. But now we basically came with a different approach because many customers are coming that we are not going to follow your traditional rules. We don't have time to do that. We don't have money to do that. Can we avoid, let's say, this inspections interval, 25,000 inspection interval? Can we skip this year? Can we skip 50,000 inspection interval to, let's say, 80,000? So they are putting a lot of question to us, and we are trying to find answer to them. And in fact, we provide a solution to them. Now we are doing, digitalizations, as I said, diagnosis methods. So putting some uh, solutions like we call uh, online monitoring systems. So online monitoring means the machine is connected with the internet. In a 1 second, thousands and millions of data feed to the internet in the cloud, and the persons like me or other experts who are sitting at the desk, different desks, monitoring that data. In addition, that Siemens has developed some artificial intelligence and machine learning tools that can predict your failure or before failure. At least it gives alarm limit that if you operate beyond that, component may fail. So we call online monitoring systems. There are various terms for them. We monitor live also, like this all needs special instruments. So you need to install new additional instrument, uh, probes. So it captures like vibration data. You install probes and it will feed to the cloud, and then I can extract that vibration data and I can take a decision that okay, vibration is not that bad. You can run the machine for a next until the vibration becomes so worse. So that kind of decisions I can provide to the customers, and based on that, they are taking that risk. So they need that support, right? Because the situation is changing, and why the situation is changing? Because of the balance between renewable. So we have different solutions right now at the moment. The one solution is the modernizations. Modernizations means we provide in older machines we provide a new component, efficient component, such a way that let's say your plant is getting old, 25 years old, so we provide a new component that have a very good efficiency in terms of power output is also increased, life is good, new materials. So those kind of new research and development can be implemented in the older power plant. So we call it modernizations. On life monitoring systems is the one terms which as I said earlier, for the last stage blade, because this last stage blade is under huge stresses, and there are probes on the last stage uh, on the last stage blade where there are probes circumferentially mounted, 3 to 4 probes are mounted. We call it a blade monitoring system or blade health monitoring systems. They can give you indications that now my blade reached to the life limit. Now you should replace the blade or you will see a failure. Then thermal twin, we call as a digital twin. That means a power plant owner can see uh, direct efficiency, real-time efficiency, and also can decide how to improve that efficiency. Which component is not, like condenser need to be cleaned up, or boiler has some issues. So those kind of things can be done by digital twin. We call as a digital real-time efficiency. Uh, you can monitor them. And then other term is asset management. So asset management is a buzzword, but it's nothing but it's a combination of all those, because power plant owners are under stress, especially fossil-based power plant, and they know that this will not going to be run for next 30 years or 40 years. They have to make money, but they have to make money in such a way that they should not fail a component. So in doing that, making money, they should not fail. They should not avoid any critical things. So we call this asset management, and we support them basically. So that is what happening in a steam turbine business and on a fossil based business in India across the globe. Now, how future will looks like? So the good thing, we have solution. So hydrogen we call as the future of the energy, because hydrogen, when it burns, it react with oxygen and it will produce only the water. So hydrogen will be replaced, currently what we are using coal or hydrocarbons, but how hydrogen will be replaced, what is the ecosystem for hydrogen, what kind of equipments. So as I said earlier, hydrogen can be used in industry, because we saw that almost 30% emission came from mobility, 23% from industry, 24% or 29% from energy, then agriculture, buildings, where we can use hydrogen as a fuel. So this is a picture where you can see uh, how hydrogen can be produced. So it's a big topic. I will cover in a short, but if we start discussing on this, we may need a 1 day, full day for that. So hydrogen is basically there are 3 to 4 type of hydrogen. One is a brown hydrogen, black hydrogen, green hydrogen, and blue hydrogen. So black and brown basically came from hydrocarbons only, and if you need to produce a hydrogen from the hydrocarbon, then you need more energy. You need to use more energy. So it's not worth to use that technology. Currently, many people are using, but that is not worth to use. It's not economical. It's not efficient method. Then other two are known as green and blue. So basically, you can use daytime, for example, solar-based power plant or wind turbine. Use that excessive electricity to separate like electrolysis process. So here you can see electrolysis process over here, and electrolysis is basically you supply electricity. So you separate water into the hydrogen and oxygen and store hydrogen for whenever you need energy or whenever or wherever, whatever term you use. So you can either pump it hydrogen to the industry. They will use hydrogen as a source of energy, or you can pump to the power plant and they can use hydrogen as a source in a gas turbine. So I will cover in the next slide how you can use. Even hydrogen started using in mobility also. We all know the fuel cells bells, Toyota car, even we see EV car from Tesla. So there we can use hydrogen as a source of energy. And even in Siemens and Alstom both have developed hydrogen-based train. So you can you know see in future a train which is running based on hydrogen fuel cell. So even in aircraft also, it's still under development. It's a very, I would say it's premature technology, but in aircraft also people are starting going to use this hydrogen. So this all ecosystem will run on hydrogen, and the hydrogen will come from, it should come from renewable energy. Otherwise, it's not worth. And wherever or whenever you want, you store it and pump it to industry. So we Siemens already started working in 2015. This is the picture in Finspång, Sweden, where we have gas turbine testing facility. So you can see the gas turbine. Earlier it was run with the hydrocarbon, right? But the turbines which are developed based on the hydrogen base, they produce the, you can see over here, the solar panels by electrolysis process produce hydrogen, and then they can run or test gas turbine on hydrogen base. So that started in 2015 only, and it's still under development. I mean, on advanced stage, I would say, not development, but it is in advanced stage. And we have product also. As a Siemens, they supplied product which can run on 100% hydrogen. So hydrogen has a one issue. The flame stability is the issue. So whatever the burner over here, flame velocity has an issue currently. So that is under development. But the small gas turbine, so this is the various model used in a Siemens gas turbine, and these are the mostly industrial application. So that means industry means you see the demand of, let's say, 20 megawatt, 30 megawatt. That demand can be fulfilled by uh, by small gas turbine. So for example, we have one gas turbine in ONGC platform in Bombay High, then Gale gas turbines, we have gas turbines. So those kind of gas turbines can run with 100% hydrogen. And the big gas turbines, so here you can see this is the most advanced version of the gas turbines, as 9000 HL. It can generate uh, roughly around 500 to 520 megawatt single gas turbine, big gas turbine that can burn 30% hydrogen, and the rest still 70% is hydrocarbon. So you can use a mixture of that, blender of that in the combustion chamber. Can reduce, you know, carbon footprint. Then uh, the in instead of using hydrocarbon, the other source of the energy also started exploring and already developed. Say ethanol is one of the source which is, you can see the future of energy. They are considered rather than burning hydrocarbon, you can use ethanol, methanol, or ammonia. Even ammonia is also considered as a source of energy. Ammonia will, separate it in hydrogen. So those kind of thing is already in a develop, and also it is developing in India. Also, NTPC already shown a interest in developing ethanol-based gas turbine, and it's a pilot project which is going to be start soon. Then this year, if you heard about the finance minister's speech in the budget, they allocated a special budget for hydrogen. How can hydrogen can be used. Already we see a development in EV cars, so this will steadily pick up, and it is a future. It is a future, sure. It is the future, and we Siemens have everything. Like we have renewables, like Siemens Gamesa wind turbines are there. So there's going to be installed onshore, offshore technology. Both are available, and from that you can produce electricity. Even solar panels, solar concentric power plants are also there. So that's slightly different than so photovoltaic, where parabolic collectors are there, and you use uh, the salt-based fluid which can be heat up, and you can store in the night. Heat energy can be stored, and in the night you can run a steam turbine out of that. And that is also installed in Israel and the Peru. So those technologies are also available. Power transmissions is there. So high voltage to low voltage, and now it's called a smart grid. Thinking about that, like earlier we as a home, everybody now starting to thinking to install a photovoltaic solar panel. So you are also producing electricity and you are also consuming electricity. So you have to maintain balance, and its balance is very difficult. So it's called a smart grid. You have to be smart, or the grid has to be smart. So it's not a high voltage grid now. It's like a generation and consumptions and they how they balance. So they call a smart grid, and hydrogen producing electrolysis technology is also there. That can be pumped to the different stations, different just like we see right now a petrol pump. In future, we definitely see hydrogen-based pump, and that can be pumped through compression technology already we have available. And storage is also done. Pipeline is also there. So all ecosystems require to set up hydrogen-based economy. It's there, and Siemens already investing huge money in this new technology. They have a lot of collaborations with different companies, and in the future, I'm 100% confidence that by 2030, 40, at least 30, 40, you will see big change in European country like Germany over there. And 2050, we will see in India also big change over here. And most of the things or entire economy will run by hydrogen. So with that, I'll end my presentation. The first part is over. Sure, what time we have right now?
Sir, we have still 1 hour left, so you may be
Mhm.
continue with the second part.
Okay, so before going second part, anybody has questions or discussions to topic?
I invited participant, those who have any question. Dharmen Tailor sir invited the discussion forum. So please unmute yourself and to ask the questions, sir. In either way, you can write your answers onto the chat box, and I will made it convey to the sir. I think, sir, there is no question from the audience, so we can
Okay,
continue for the further.
okay. So the next topic is, I think, it's vibration diagnosis is the next topic, right?
Yes, sir. Yes, sir.
Okay, just give me a minute. So the next topic is the rotor dynamics and vibration diagnosis. Again, it's a very diverse topic, and I will touch upon the introduction part only. Will not go in much detail. Um, it's difficult to cover in 1 hour, so that's the reason. But if you have any questions, feel free to ask. I will answer. Try to answer your question as best as possible. So I think we no need to cover over there fundamental or vibrations. So normally why we need to measure vibrations, and we I think touch upon something in my last presentation also, that the rotary machines typically we don't want to fail. We want to measure it, and uh, we want to run it continuously and generating electricity or making money for the power plant, and we don't want to stop it because of only vibration issues. And if vibrations are there, then because it, rotor and the blades and the casings are very they have very less clearance in terms of the number. If I'll talk about, then it's less than 1 millimeter gap during the operation. So if it is rotating at a 3000 rpm, and if it touch to the stationary part, then either material rub, wear, or you will have a failure happens. Blade will fail or blade will deform. So we don't want that, right? And we want to stop the malfunctions. Vibration also gives these conditions of the rotor, like normally if there is a vibration in the systems, then it gives indication that there's something wrong in your rotating systems, either it is crack or unbalanced or whatever reason. So the vibration is the output of the something happening over there. So there also we need to measure it. If we don't measure it, just run the machines, then it's not good. So before getting big failure, we need to resolve that problem, and that's where the diagnosis part is always play the role. So we all know this fundamental of vibration. I will not go to the in the detail, but this is called rotating systems, simple rotating systems, and it is called a Jeffcott rotor. Jeffcott is the persons who was, you know, developed the mathematical model, and there is a good history behind that also. So uh, in 80s, I think 80 somewhere, uh, or before that, uh, we all know Rankine cycle, steam turbine cycle. Rankine was the principal royal, principal engineer of Royal Society of Mechanical Engineering in UK, and he said that rotating machine cannot be run at the certain speed. If you run it, it will fail. And when he said that, because his reputation was so high at that time, nobody was challenging him, and people start believing in him and believing in his theory that you cannot run rotating machine. So that entire era where where we saw a lot of development in reciprocating engine, but in rotating engine, we don't see any development. uh, that was the main reason that people were believing Rankine, that you cannot run a machine at a certain speed, otherwise it will fail. Until the independent developer like Strodla and others like Skoda, they are uh, different country from different country. They were also developing rotating machinery, and their machine run more than 1000, 2000, or 3000 rpm or 10,000 rpm. And when they came up with their research, and they said that there's nothing happening over there. So then everybody's looking over there, and why it is it not fail. I mean, what happened over there? So Royal Society of Mechanical Engineering UK started funding this program, and they hire engineer Jeff Cott in 1930, I think, or 1920. So he hired for develop a mathematical model for rotating systems, and what is that the speed where you cannot run. So then he started developing the mathematical model, and he developed that, and then he proved that by calculations, those speed is nothing but it's the critical speeds where we see response, where we see resonance. So to give a tribute to that entire development, um, we call this one disc shaft is called a Jeffcoat rotor. So Jeffcoat rotor equation of the motion, we all know this is the equation of motion. So it contains mass, damping, stiffness, and force, unbalanced force or external force. If it is zero, then we know that it's a natural equation of natural. Uh, if you solve it by, then you will find out the natural frequency of the system. So but in the rotating system it's slightly different. So it's depend upon stiffness. So what is a stiffness? A stiffness is something which is coming from the rigidity of the shaft. So just like over here, if you apply external force, the deflection over here shows that force upon deflection shows the stiffness. So similarly over here, a rotor try to rotate, it try to deform also in any directions, right? So that is gives a stiffness. While damping over here, if you have a rigid supports, almost no damping in the systems. Most of the damping coming from the frictional forces or inherent material damping. Apart from that, mass is clear. The mass of the system is nothing but the volume and the density. So if you ignore this, the equation becomes simple, and then you can solve this equation, and omega is equal to square root of k by m. So by solving that, you can derive the frequency of the system. But in rotating body, it's slightly different, because uh, I will touch upon that. So yeah, before going that, the spring mass systems, like you can see over here, when there is a resonance, then it will start vibrating a lot, and it is vibrating like this. So but in a rotating system, it's slightly different. And why it is different? Because they have a different mode shapes. So there are two terminology. One is called lateral, and then other was the torsional. So lateral is nothing. Lateral is nothing, but lateral is the motion in a vertical plane and horizontal plane. So one is a vertical plane. So bending happening in vertical plane and bending happen in the horizontal plane is called a lateral. Like twisting is what? Twisting is just imagine that this is twisting in positive direction and this is twisting in opposite direction. So that vibration is called as a twisting vibration. So lateral vibrations, so we call horizontal and vertical directions, and twisting is a twisting movement, theta movement, motions which we are mostly interested. And if you forgot about the torsional, then in the lateral also, um, it's where the oscillation happen in system is just like moving at particular fixed position or reference position. Either it move up and down, right? That we know. But in rotating system, it is not like that. So in rotating system, there are two speed or two motion. We call a whirl motion and rotation. So what is whirl motion? So that means there are two rotation. One is this shaft is rotating about its own axis, right? This is its own axis, and then it's also entire shaft is also about certain axis. So here, when while rotating on this axis, sorry, so it is still rotating. So rotating means RPM. So whatever physical RPM it's rotating. By whirling can be happen at the same speed or different speed also. So not necessarily it is happen at the same speed. So here you can see this is my center of and it is rotating. So here it is rotating. But while rotating, it changing its position and also rotating. So if it is rotating in both the same direction, rotation and whirling, then it's called the forward whirl. But if it happen in the different direction, we call a backward whirl. So the classical example, sometimes if you observe closely with the fan, then fan is if you see closely, then sometimes you think like it is rotating in opposite direction, and all of a sudden it stop and rotating in a positive direction. So typically it happen while switching of the fan uh, pass through the critical speeds. So when it pass to the critical speed, probably you will see this kind of wall motions. And in real life also, fan is vibrating, but the whirling is difficult to visualize because probably it is designed such a way that we can't see the whirl motion by our naked eye. But there are some whirl motions, and that's the reasons it is vibrating. But while stopping the fan, From its rotating speed to the zero speed, it may pass maybe one or two critical speeds. There you see such kind of motions. So in rotor also same thing happen. There are two motions happen. There's a vibration. The vibration is nothing but the distance between this my center position, is my world position, is called my vibration level. So that means my rotor is vibrating in vertical direction this amount, or by 2x or 2y I call this amount, or in horizontal direction it is this amount. So this is my vibration. So if I'll put a probe over here, let's say my probe is there and here. So probe will measure x directions. So this is my total motion of the vibration rotor. So it's nothing is a vibration. So if I'll put a probe over here, it continuously moving here and here, right? So that will give you a sinusoidal wave, a sinusoidal output. Similarly, if perfectly it is vibrating like this, like continuously it is moving like this, then if I put a probe when rotor is over here, maybe it's a zero or minimum negative distance from this point, it is negative distance, and when it passed to here, it may go to positive distance. So if I put a probe over and over here, then I will get a two different sinusoidal wave, and amplitude of that is depend upon the how much whirling happen. So even the whirling, it can happen with the different shapes. Like a rotor can obtain a different shapes. Uh, like one part of the rotor is whirl happen in the positive direction or forward direction, one part of the rotor whirling in the negative direction or backward whirl happening. They have also different node points, so obtain a different shapes. But the fundamental mode means initial two modes are cylindrical mode. So because either entire rotor is rotating, whirling happen in this direction, or conical mode where second mode we call it where second critical speed, where the center part is rotating at the zero, and the bearing ends they are having the highest vibration, and other side of the bearing have other directions vibration. So this is two fundamental mode, and in real life it is not look like that. This is theoretical representation. In real life it is totally different. It's a very complex behavior. So then how you do in calculations, like when I am doing any calculations, how I will do. So this is actually when recently we installed in one of the power plant. So this is how it looks like. This is a rotor body. These are the blades you can see over here, blades. So rotor body is supported on a bearings. So this is bearing, fluid film bearing, hydrodynamic bearings. And while passing through the this is the representative of the rotor. So I need to have two things. One, in fact, three things: mass, stiffness, and damping. So mass, I can calculate mass of the rotor from its geometrical parameters and the mass of the blades. So I can calculate the mass, and the stiffness is here. You can see here, stiffness is not same as a mass. The stiffness resist your distortion. So that you cannot calculate. You have to calculate strain energy. So that can be done through FEA only. So we perform FEA, finite element analysis. You calculate the strain energy of the each component, and from that you can come to know that what is the stiffness of that particular sections. So here you can see this is the my blue line is the mass, and this is the red line is the stiffness. That's how you calculate the stiffness. So what that means? That means the mass over here that doesn't contribute any stiffness. Mass over here doesn't contribute any stiffness. But here you can see any change in rotor geometry will not only change the mass but also change the stiffness. So uh, to give just idea that if you have a crack over here, if you have a crack over here, it will change the stiffness of the system. So it will change critical speed of the system. But if you have a crack over here, somewhere here, it will only change the mass. So in result of that, you will see unbalance in the system. So it will not change any critical speed. It will see the vibrations. But here you will see shift of the critical speed as vibration also. Then coming to the damping dynamic part. So damping come from the bearing. So bearing is looks like this. You have shaft, you have oil fin, and you have stationary component. oil film is this is the clearance, right? And the clearance is the here typical clearance is the point or 70 micron. That's it. It's not more than that. So the minimum film thickness over here is a 70 micron only. So everything happened over 70 micron, and that 70 micron contribute damping as well as the stiffness also. So this is most complex over here in rotor dynamics. They have 8, 4 stiffness and 4 damping, and each parameter affect speed differently. So we use CFD method to obtain the damping and stiffness of the system, as well as we program. So after doing that, after solving that, your motion is equal to 0. So you consider no external force. That gives you natural frequency of the systems. And as I said earlier, here it will come whirling of the motion. So this shaft, if it is rotated at the first critical speed, which is around 19 hertz, then it obtains this shape. And that means the whirling happen at all sections, but at the center it is maximum. At the bearing is the minimum. First mode, then second rotor obtain this S kind of shape, so we call S shape also. And here you can see at the center, if you put a probe over here, get a vibration 0. But if you have probe at the bearings, you will have vibration, highest vibration. So because you have highest whirling happening over here, right? So that is called S mode. And this is exaggerated view, and this is a real when with shaft is vibrating, uh, it will obtain these shapes, right? So you will have a change in the phase angle and all those things that you can come to know. Now next part is unbalanced response. So unbalanced response is nothing your external force, where we ignore 0. Now we applied external force. We estimated external force based on the design of the rotor and apply to and excite the system and see how the response of the system, how it will respond in real life. So this is the theoretical response, and we see the theoretical response. Let's see here, we see resonance, we see resonance over here. That means we know some critical speed over here. We have critical speed over here, but our intent to design is the 50 hertz. So let's say if it is running at the 50 hertz, we should not have a critical speed nearby the 50 hertz. So this is how we are designing. And if the critical speed is nearby, then we have to change the design. So this uh, design of the systems will take a lot of time to fix it, because you are not going to change design by your own, because there are other disciplines also working on the rotor design, like blade engineer is working on a blade design, and he or she choose diameter such a way that it will give you maximum efficiency. And now you say I am shifting my diameter to over here, you will say no, because I will not get a space, or I will not efficient design. Then it's iterative process, and it normally in R&D stage, if something happened like this, then we call a tuning of the rotor. So that we that this critical speed shift away. It takes maybe a year also. So this is about the theoretical, and the dynamics of the systems almost come from fluid film, uh, even steam valves. So that means the steam also act as a dynamic damping, is acting a force on the rotor. And the leakage from the seals also act, because very narrow gap between the rotating and stationary component, and there are many turbulence over there, so they act damping in the rotor, and small change in the gap will entire behavior. So that is also very important. So if I compare with the stationary component, we call vibration in a stationary component. If you make that spring mass system is vibrating like this, but in a rotating system it's a whirling. So it's not a vibration, but whirling happen. In stationary component it's a natural frequency, whereas in a rotating we call a critical speed, where the resonance should not where the resonance, and we should not allow rotor to rotate. Then the mode shapes, we know the mode shapes, how the spring is vibrating, sometimes vibrating like this, sometimes vibrating like different way. Here there are motions, cylindrical motion and the conical motions. Then amplitude of vibrations, amplitude of the whirl is important, where we are measuring probes, through probes we are measuring amplitude of the whirl and mass unbalance. Uh, Normally external force which excite the systems are balanced, but there are other forces also. So oil whirl, whip, steam whirl, and those things. So how bearing looks like in a system, the way we use types of bearing based on the configuration of the turbine. Mainly also fine-tuned bearings. It's optimized bearing we use. Then tilting pad bearings, where the multiple pads are used, which are supported and which are acting pivoting actions. Uh, those kind of things used in the design. And then uh, this is all about lateral. Then torsional. Torsional is, as I said earlier, twisting of the motion. So twisting of the shaft. So even shaft also vibrate in other direction. Like during the vibration, some of the rotor twist in a positive direction. Like 6 hertz, as the 6 hertz, you can see here the other part of the rotor is moving in other direction. So and if twisting happen, let's say you rotate or not rotate, but excitation coming at the 6 hertz continuously, then your shaft will break over here because you will have shear effect over here. And the most dangerous things for the rotor is the torsional or the twisting of the rotor. And normally that happens, and that happens in a few accidental event where the is the almost 7 time 8 time then the nominal torque happens, and that happen in very narrow time frame. Let's say zero point 0.2 or zero point 0.3 seconds. If your shaft is not designed for sustain that load, then it will take in two pieces, and that happens in the past also. Old design we see rotor breaks in two pieces. Even blade also. So here you can see this is by the way, this is the rotor train of a nuclear power plant in the USA, where I have performed this torsional calculation. And you see these are the blades. Last stage blade also have a very big inertia, and they also try to vibrate. So they vibrate in positive direction, negative directions. If that happens continuously, then imagine that it has every rotation, positive and negative, it will fail instantaneously. We call it the high cycle fatigue. So we don't want to do that. Um, Now, what is the timeline for this lecture?
Timeline is, sir, up to 2:45.
Okay, then I will continue.
Remaining.
Thank you. Okay, so now that is design part where we take care rotor dynamics, but we know even you take care many things in your design or everything in the design, still you will have a vibration. You cannot nullify the vibration, and it's not only depend upon the design, but then it's also depend upon the how you do maintain. Many like almost 33 34 reasons in our root cause analysis where they are acting as source of the vibrations, and there are few very common 10 zero down over here. Unbalance. So unbalance means mass unbalance means rotor is perfectly balanced in the shop, but that is happen during the supply of the rotor. But in operations, normally they get rubbed at certain locations. Some deposit happen, some wear tear that happens with the rotor, and because you will see continuous unbalance in the system. So that uh, if that is happening, then vibration will come, and you will see of either critical speed at a nominal speed, also you will see high vibration. So that can be rectify or balancing of the system. So you have to shut down the shaft, and then there are provision where you can put a mass a balancing weight based on the phase angle and amplitude. You can decide where to put which locations based on the rotor dynamics, mode shapes, and all those things. And that way you can rectify the unbalance in the systems. And typically every plant they do this balancing short activity after certain interval. The other most common reason is a misalignment because the rotor is not a single rotor. It is coupled rotor. It is connected with the multiple rotor. I would say that in normal rotor train, where you have 3 LP, 1 HP, 1 IP, generator, exciter, 6 rotors, 7 rotors are connected each other, and it's a big rotor train. The distance between one end to another end is sometimes 40 meter, 50 meter also. So you can imagine it's a big rotor train rotating at the 3000 RPM, and they are coupled with a bolt. So how accurately they have to align? We are talking about the microns. If they are away certain microns, then you will see resonance or act unbalanced force over there. So misalignment is the very most common, and what happen is the normally in the maintenance when there is outage, there is always pressure to bring a machine back into service. People don't focus on the alignment, or they don't achieve what the desired value, and then they start the machine and uh, they have vibrations. So this is the most common. Eccentric rotor or band shaft is the another rotor. This can be happen like two things. One is when the rotor is started heating up, because it's subjected to 540, 560 degrees Celsius. Thermal expansion is uneven in the system. If soaking is not properly done, then shaft will bend by certain um, point 2.3. Eccentricity will be 0.6, 0.8. So this nominal 0.6, 0.8 mm is also create high vibration in the system because it's a huge mass. Uh, by the way, the mass of the rotor is almost 70 ton or 80 ton. So 80-ton rotor is rotating with a 3000 RPM or 3600 RPM. The forces on the bearing pedestal or bearings will be very huge. So if any eccentricity in the rotor due to thermal bow will also result in a vibration. The other reason is band shaft. Band shaft could be a permanent band also. What is happening is like many old power plants, the materials is based on the creep vanadium based material. They are supposed to withstand this high temperature, but over a period of time, their grain boundaries are starting dislocating because of the creep effect. So they are starting permanent band, and I'm talking about very nominal band, and this nominal band also cause zero point 0.1 zero point 0.2 millimeter vibration in result. Then mechanical looseness, weakness or pedestal looseness is also very common. Wherever you see, you also you can see in normal life also, where motor or pump is their foot are not properly tight, or the bolt are loose, or that their foundation are weak. Over a period of time, what is happening that the foundation are getting settled down because those are supported on concrete pillars, and these are big pillars, but after 20 years they got sagged, they got going down, and this is very zero point 0.1 0.2 mm only. So relative height between pillars are different, and because of that you will have eccentricity or you will have excitation in the systems. So that is one reason. Then bearing itself got wear and tear. So the parts are on the contact, they are losing the context, they are deforming, they are slipping over there, and so they are not behaving as what they desire to do. So that is also reason. Then resonance of vibrations. So there could be any of above, like unbalance or whatever reason. Rubbing, yes, this is also common. As I said earlier, the clearance between the rotating and stationary component is only a point less than 1 millimeter. Now, small rubbing happen. What will happen that particular local region become very hot because of the frictional heating, and that try to deform more. Now, when this happens, that deform more, they try to expand more. So what happened that the gap between this rotating and stationary component get bridged, and more rubbing will happen. So you will see that local portion become very hot and it try to bend also, that we call a hot spot. And because of that, you will continuously see change in the vibration behavior. And so clearance between stationary component and rotating component is very important. Uh, we often see such vibrations in the new machine also, in the old machine also, because new machines, what happen when during the assembly, the clearance are very tight, the main to be tight, because we want high efficient systems, we don't want leakage losses. And by doing that, if you have small vibrations started somewhere, you will see a rubbing and then hotspot and rubbing again, vibration, and these are the cycle continuously running. External force from the pipe, yes, there are piping structures connected with the steam turbine. They also try to expand, thermally expand, and when they expand, they try to push or pull the rotating and stationary body. And when while doing that, your alignment will disturb between rotating and stationary component. Then these rotors are supported on journal bearing. So journal bearing has their own complexity. Like we all know, it's lubricated by oil film, oil supply, external oil supply, now oil quality, oil temperature, oil type. This all impact my rotor dynamics, and I will see vibration over there. Even some instant you will start seeing bearing temperature start increasing, or sometimes certain temperature is going down and certain temperature is going up. Erosions you will see in the bearings itself, uh, because of alignment bearing try to get low. These are relative things. It cannot start with the one thing. It is possible that in a system is vibrating due to multiple reason, and you have to when such problems comes to you, you have to think all possible reasons and address all possible reasons. Then only you will resolve the problem. uh, Very likely that uh, that resolve in a one shot only. It is not possible to resolve in one shot. Many times it is happen that because of the multiple reason the vibration in the systems are there. So you have to address one by one. So it's like you have to prepare a checklist, and you address one problem, address that issue, you see benefit, you do it. If not, then address other issue. So high load, as I said earlier, the bearing is very sensitive. A small movement in the bearing result in a huge significant effect on the vibration. Oil whirl and the steam whirl is a different source of the vibrations, where fluid and structure interactions. Fluid and the structure both have a fluid structure interaction starting different behavior, and they are producing vortex in the systems. So there's those kind of things will also source of the vibrations. Oil quality, I say that oils normally due to frictions, they are getting heat up, and exhaust temperature of the oil will be in range of the 80 to 90 degrees Celsius, and they need to cool it to 40-43 degrees Celsius. So what is happening is it passes through the cooler. Now many times coolers get punctured, oil and water get mixed up, and the viscosity, whatever required viscosity, that getting reduced, and you will not get a desired parameter what you want. So that is also possible. Sometimes foreign particles come in the oil, filters are not working properly. You will see a wipe out in the bearing or scoring mark in the bearing, and because of that, now the clearance between rotating component and stationary inside the bearing is only 70 micron, and that get changed. So you will see the change in that all. You will see the change in all these 8 component, and that change my critical speeds and change in the damping. So these are very sensitive to this particular clearance over here, and you will come to only open the machine and inspect the machine, then only it's sometimes possible to know. Otherwise it's very hard to know why it is happening, right? And aerodynamic, yeah, aerodynamics within the blade also uh, getting forced by steam and other things. So that get flow turbulence, flow separations within the steam that excite the blade, and blade start vibrating, and in a result you see a vibration in the rotor. These sometimes industrial applications steam turbine, they are connected with the gearbox. So gearbox have their own problem, like because wear and tear is there. So they sometimes crack, backlash happens, misalignment happens. So those kind of vibrations is also there. So this is not a one list. There are, I said, 40 or 30 more than that possible reasons you have to work on. Then how you do in real life? Then we typically use two probes, proximity probes. The proximity probes are basically measuring the vibrations. So basically they are measuring the AC current and DC current. AC current is nothing is the vibrations, but DC current is a south central line position. And then accelerometers are also used to measure the pedestal vibration of a stationary component. And then from that you can use the relative. So this is absolute, then you have relative, or relative to absolute, whatever you can say. You can do it by using two separate probes. And for the rotation, we use the key phase, and there you can come to know that at every rotation you see a such signal, and from that you can measure RPM of the system. So if let's say power plant is having vibrations, then we have this vibration portable vibrometer. You can carry these vibration probes or meter to the site, extract the data, do a post processing, and then from the post processing you will come to know that what is the possible reason. So normally balancing engineer carry this meter or this machine with them, and they extract the measurement and then they share with us, and we do diagnosis. Based on that we propose the solution. And as I say earlier, uh, the remote diagnosis. So this is what remote diagnosis looks like. The plant data are extract, and there's a server control systems T3000. It can send. It is connected with the internet, and it can send to cloud uh, thousands and thousands of data, temperature, pressure, vibrations, whatever probes. You can set the signal limit also, and that data sent to the from the control room. It's sent to the cloud. And in the cloud, we have developed special softwares based on artificial intelligence and machine learning. You can predict a failure, or you can predict machine behavior. So this data either it can send globally anywhere based on the depend like need of the customers or agreement between customers. So we have centers like a power diagnosis center where engineers like us sitting over there, and they are extracting data daily basis, and they are recommending customer that how they are operating. Sometimes customers are very smart, follow the rules whatever the we mentions operator mentions, because of the in a hurry to bring the unit back into the grid. So those kind can be predicted, right? Now uh, diagnosis um, diagnosis need data first of all, then only you can perform a diagnosis, right? So diagnosis, like suppose you have fever and you go to the doctor, and doctor says that you do MRI, you do CT scan, X-ray, echo. What is this? Everything is the instrumentations. They need something data to come on a common conclusion. They need evidence. So in a diagnosis also we need some sort of data. These are not the limited one, but we need many others also. An important thing for operator who are operating the machines, they should store all data with the proper fashion. If they have data and they are not storing properly, and then they face the issue, then probably it's difficult to come on a root cause. Otherwise, you can guess and then provide a solution. But proper diagnosis, as I said, also reach common conclusion. So vibration, temperature, speed, phase angle, load, pressure, past maintenance data, past alignment data, checklists, clearance calculations, clearance sheets, all those things are needed. Then only you can do analysis. And this is in fact very deep topic how to do, and normally level 3, level 4 vibration experts are doing this. So this is in fact it's a 5-day program where people are doing this. So it's difficult to cover and just give you the glimpse that what kind of data we are doing. Time domain, that means the vibrations across the time. It is plot across time and see how vibration behavior is, any abnormality. Based on your experience, you come to know that these machines typically run with such vibrations or such level of vibrations, and all of a sudden you see jump, all of a sudden you see step change. Then you come to know that at that particular time something happened. So that can be known from the water plot or a time dominant plot. Then frequency, so you extract the data and then you Fourier transformation. So from that also you come to know that which frequency involved in that vibration. Uh, 2x, multiple harmonics. So those kind of things you can do. Then orbit domain. So you can see the go to the slide. Yeah, you can see how the rotor is rotating clearance, bearing clearance. So this is my rotor and this is my bearing clearance. How rotor is rotating, so how whirling is happen, as I said earlier. So based on external forces, the whirl behavior will be different. And here are some of the reasons you can see: rotor rub, bearing loading, unbalanced, misalignment, oil weep. This change my rotor orbits. Orbit is nothing but the if I'll track this my center point of the shaft and how it behaved during my one rotation. So if let's say this is a rotation, then whirling may happen like this way, right? This is different direction, different rotation. This is rotation which you measure in RPM is different. So from that you come to know that what exactly is the problem within the system. And then the polar plot is the nothing but it's vibrational data with respect to RPM you plot in a polar coordinate systems, and that gives you indication like where is my critical speed. So from here, if you put a probe over here, the orbits or the vibrations looks like this. Then here maximum vibration is happening, and then phase change happen. So same way with the polar plot, and come to know that what is happening in the system. And then next one is the soft central line. Soft central line is the again this soft center position. If oil start flowing within this convergence, then fluid film become over here, and this is slowly rotating. Once it start rotating with the high RPM, slowly it is changing its positions based on the flow of the oil. So here is based on the rotation, it should go up and take a load. So why it is going up? Because the fluid film becoming over here. That's the reason it's going up, right? Somebody is sitting over there, which is film. If that is not happening that way, if it is happening way like this way, something like this, then you come to know that oil film is not working properly. Something, the loading of the bearing is not proper. So those kind of evidence will help you to diagnose the problem. So the next one is the frequency domain. As I said earlier, vibration is not a single vibration or a single frequency domain vibration. It's a mixture of everything. It's just like it's a sound when many people are sitting together, and if everybody is talking, then sound is a mixture of all. But if you want to interested in specific sound, then let's say the person X is talking like this, then person Y is talking like this, and person Z is talking like this. If you're interested how Y is talking, then let's say X and Y separated, X and Z, and how Y is talking, you interested in that frequency. So that is you can do by frequency analysis, FFT analysis, and from that which frequency involved, like given here, like frequency involved, then looseness is there, and sometimes I don't have the plot, but subsynchronous vibrations are there. Like so, as I said, it's complex thing, difficult to explain in 1 or 2 minutes, but yeah, you can do by that also. So with that,
just minutes time remaining. Taylor,
yeah,
sir.
I am already done.
Okay,
I am done.
okay.
I am done. So with that,
Okay, thanks.
I'll thank you all for listening me for almost 2 hours, and I hope this is interesting you, and it will help in your future. Over to you, sir.
Okay, thank you, Dharmen Tailor, sir. You explained very well about boiler operational aspect. What are the different aspect of energy scenario in India on basis of current as well as for the future, and you have also cover up some new site erection at the different parts of the country by stating suitable examples and by giving tabular and graphical data. Later on during the second part, you may have consider the uh, vibrational diagnostic part for the rotor dynamics, turbine, etc. machinery in the power plant. So that is a very useful knowledge as we have taught undergraduate level 1 course power plant engineering. So that syllabus covered under your session today is beyond our reach while our primary syllabus of the university. So I am very thankful to you for speaking constantly and showering the knowledge to us over the time period of you can say 120 minutes and more time. So the participant of the uh, faculty development program enriched their knowledge with your expertise. So we are very thankful to you, sir.
Thank you so much for inviting me. Also, this is a very good platform where I can interact with the people.
By inviting a participant, is there any question so that we have just 2-3 minutes remain to end up this session? Any participant having any query question, then sir will have incorporate your answer. Otherwise, we may have to end up this session now. Participant, is there any query? Any participant has any query related to the discussion made in the today's expert session? Okay, thank you, sir. There is no query from the participant.
Okay, thank you. Then, if there is no question, then I hope it is understood well.
Okay.
And yeah, thank you.
Okay, thank you, sir. Now, participant, we have to end up our this session now, and you are requested to join again at 3 o'clock, where we have the session of Mr. Verma, sir, from Director of Industry, Oil and Gas. Thank you.
Thank you. Bye.
Again, I requested participant to join exactly at 3 o'clock. Thank you, friends.